All right, so trees, like any other data structure, may want to have some order. So there's going to be more than one way to order data in a tree. Some trees will have left to right data relationship. Some trees may have an up-down relationship. All right, so we don't have just a simple nonlinear structure where we have the smallest at the front and largest at the end, because right, we're going to have more than one end. So a binary search tree, this will build with a left to right ordering mechanism for values that are lower and a root in the tree has values less than, or excuse me, I already said, those are lower than the tree are on the left side. On the left side, values that are greater than the root fall into the right side. All right, so building a binary search tree. First value that comes along will become the root. And we'll continue building the tree starting at the root. As new data comes along, compare that data to the root and either traverse right or left based on the relation. All right, so we build our tree 20, 30, 15, 40, 25, 10, and 12. Our first state, go ahead and make 20 the root. When our next data point comes along, we have 30, we'll compare 30 to 20. 30 is greater than 20, so we'll go ahead and have that. Go ahead and go to the right side. The right side of 20 is empty. So we have room to go ahead and splice 30 onto the tree there. Next up, 15 comes along. We want to enter that into the tree. So we'll compare 15 to 20, 15 less than 20. So we want to attach that to the left-hand side. Since we have no tree on the left-hand side of 20, we can go ahead and just attach that into our tree. And we'll keep on building. 40 is our new data point. As we continue to build a binary search tree, we're building it in a top-down fashion. Start at the root. Compare. 40 is greater than 20, so we'll go right to the right. We already have the root of the 30 subtrees. We'll go ahead and compare again. And we'll go right, and then we have 40. We're here on the right-hand side. So we'll go and take a pause at this point. We look at the overall tree. Right, from the perspective of the root, all the values in the left-hand side of the tree to the left of 20 are all values less than 20. All values to the right-hand side of 20 are going to be all our values greater than 20. For the moment, we're going to not allow duplicates because duplicates are going to just degrade our tree structure. All right, 25. New data points coming along. It's greater than 20, less than 30, so we're going to go ahead and attach it to the left-hand side of our 30 node. And we'll keep on building. Let's see. Squeeze 2 more in here. Kind of, sort of. All right, 10 comes along. Again, start at the root and compare. 10 is less than 20, so we go left. 10 is less than 15, so we'll go left again. We have an empty position. So we can go ahead and attach to our tree. And we'll need to do a little bit of squeezing here, but 12 is up last. Less. All right, less than 20, so we move down, see where's it go in the 15 subtree? It's less than 15, so we move down. Where's it go in the 10 subtree? It's greater than, so it goes ahead, goes to the right. Just redraw our final products. We can go ahead and line things up a little better. And reattach. Okay. So like we had before. Okay, let's try that again. All right, all the values less than 20 are in its left subtree, right? 10, 12, 15, all values greater, 25, 30, 40. That same relationship holds for the root of every subtree in this tree. 15 with the root, all values less than 15 to its left. 10 at the root, all values less than 10 to the left, there aren't any, and greater than 10 to the right. All right, 12, and so on and so forth. 30 with 25 and 40. And subtrees, and of course our leaves have our empty subtrees. We'll do more with bias virtues in a little bit. Another way, order our data, binary heap. Ordering in a binary heap will be with an up-down relation. There will be 2 specific types of binary heap. Min heap, where we keep smallest value at the top, and max heap, where we keep the largest value at the top. Okay, so build again in a similar way. One of the differences we're going to see here as the heap builds is it's going to build in a very ordered fashion. So 20 is our first value. In fact, let me go get my numbers. We can build them in the same order. All right, single node by itself What does a heap mean? Heap's just the name of this tree structure. Just like you have a heap of clothes or a heap of trash, basically a pile. And a heap of trash tends to want to form into a bit of a triangular formation, just like trees do. So when we have a one node tree, whatever sort of tree it is, that's pretty much the only shape it might have. And the way that we're going to be building our heaps is we're going to be building it in a specific order such that we are going to maintain that triangular structure as perfectly as possible. So as we build the tree, we're going to be building it level by level, just like we were doing with the array-based tree lab. So as our nodes come along, we're going to add them. So right now we're doing a min heap. So let me add that context, min heap. So what we want the relationship to be is we want the smallest value at the roots. Right now we have two nodes in the tree, 20 and 30. 20 is smaller than 30. So it's happy with the relationship. As new data points come along, we want to add them to the tree. We're going to keep building it in a level by level format. As we add them, we're going to look and see if the data relationship is maintaining the way we want, which is known as a heap property. I'll write that down later. If the data relationship is not correct, then we're going to rearrange the values so that maintain order, and the order is going to be in a vertical path. So if we take a path from the root down to any leaf in the tree, we'll have a non-descending pattern. The heap will allow duplicate values just fine. We'll get into that later as well. But 1530 going up, 1520 going up, and we'll continue doing that each time we add. Whenever we want to add to the tree, we're going to keep building it level by level. And as we're building it level by level, we're going to go from a left to right pattern. All right, so we added 15. 40 is our next data point. First level is full. The second level is full. So we're going to go ahead and build up to the third level. 40 is going to look at its parent, test to see if the relation is good per the requirements for a min heap. And since 40 is greater than 30, we're good where it is. And we can go ahead and continue on. All right, 25. Keep filling the level as we fill. Let me make a copy here. As we fill, then we test, make sure our relation is good. If it's not good, then we're going to have to do some swapping of our data here, or heapifying, where the value moves up. So 30 was too big, so 25 moved up. And then we'll go ahead and look at the parent, 25 is going to see how far it can push its way up. And it has no further it can push, so it stops right there. And that's enough. That screen's getting going. Excuse me. All right. What was our next data point in order? 10. All right, 10. 10 wants to add such that we're filling the next level. It is going to test its value against its parent and see that that relation is not correct. So 20 is going to move down. Excuse me, 10 will move up. And it's going to test the relation with its parent and see that that's not good. So it's going to move up again. 10 moves down, 10 moves up. 10 sees that it's at the root, it's getting no further than it can go, so it stops right there. And then lastly, 12 will be added to our tree. Last possible position in our lowest level will be where we want to try to put it. But we'll see that that relationship with its parent is not correct. So we'll move some data around. 15 will slide down. 12 slides up. We will test 12 versus 10. See that our data is in appropriate relation. And we're good to go. So if we trace down any path, 10, 25, 40, 10, 25, 30, 10, 12, 20, and 10, 12, 15, right? They all go in this ascending, because I don't have any duplicates, order. Okay, so let's dig deeper into those two tree structures. All right, so the binary search tree. All right, again, we have our left to right relation. The smallest value is the leftmost node. The largest value is the rightmost node. And in order traversal will produce a sorted set of data. All right, so let's do some tests. That's not the word I'm looking for, but checking on these trees to see if it meets the conditions of binary search tree. All right, so it's a binary tree, so it's our foundation. All right. Where's my numbers? There we are. All right, so our first tree here with just 50 in it. It's by definition going to be a binary search tree. Because there's no other possible way we could arrange that data. All right, 50, 45, still binary search tree. It's got one other node. What about my third tree here? Is this a binary search tree? With 55 to the right of 45. Let's see. I forget, what are the raise hand options? What are the little icon options? Yeah, raise hand. What other shapes do we have? So when everyone can toss their vote in. Thumbs up and thumbs down. Okay, so Thumbs up is yes, it's a binary search tree, and thumbs down, no, it's not a binary search tree. It looks like it's nice and anonymous too, so people don't have to worry about, is there only thumbs up or is there a thumbs down option? Okay, good. There we go. There is a yes and a no. All right, so yes is thumbs up and no is thumbs down, I suppose. Ghost is it's in multi-states at different points in time. We do that as well. All right. So if we look at this part of the tree, look at our subtree here, which is typically drawn as a triangle, crudely sometimes. 55 is to the right of 45. So this subtree itself is a binary search tree. So that is good. But when we come to the 50 state, everything to the left of 50 should be less than 50. And 55 is not less than 50. So it's found its way into the wrong side of the tree. And so when we added this, we didn't want to continue from where we left off. We wanted to continue back at the top and then do our data comparison. And then we would have taken our 55 over here to the right-hand side, right? And so that tree is breaking the search part of the rule. So it's still a binary tree. Right? So we're like asking a test question, what kinds of tree criteria does this mean, right? It's a binary tree because we see at most there's one child and it's at least drawn in a left-right orientation as opposed to just a straight line, which we wouldn't be able to differentiate from just a list. So it's a binary tree, but it's not a binary search tree because 55 is out of place. So now here's the next question. Is this a binary heap? And go ahead and do yes, no, or thumbs up, thumbs down, whichever. See if we have that proper order. So do we have are we ordered in a way, just looking at the data for the requirements of a heap? All right, so when the way that we check is build a path from root to every leaf. And if it maintains order on each path, then that ordering is good. All right, so we went from 50 down to 45, then up to 55. So this is not going to be a heap. And let's do another tree here. Let's fix this one. All right, we already know 55 is wrong, so we'll move that into place. All right, now we have back here a binary search tree. And add 25. Okay. Go ahead and clear that. Let's try that again. All right. How about our fourth tree, binary search tree? Do we have a proper left to right? Everywhere that we look left and everywhere that we look right, people are in their appropriate set of data. And it's okay to be wrong. The trick to being wrong is figure out why you're wrong so that the next time you're not going to be wrong. All right, so again, left, right, and we do need to do left, right at every root in the tree. Everything greater than 50 to the right, good. Everything less than 50 to the left, good. Okay, do it again for 45. To the left, good. To the right, okay. Because there's several ways, several opportunities to break the tree. All right, so let me go ahead and put a mark that one as bad. And let's add 42 here. And all right, got another tree. First off, is it a binary tree? Do we have any node here that's beyond our rules of being a binary tree? All right, root's got 2 children, 45 has 2. The other 3 nodes are all leaves. No, the test next week is the rest of our linear stuff. Double linked lists, sorts, reverse Polish. Yeah. We're in section 3 here, so that'll be on test 3. Remember that the notes pages, the first part of our numbering system indicates the section, and each section has its corresponding test. All right, so we've got a binary search tree. Excuse me, we have a binary tree. Now, next question, is it a binary search tree? Yes, no, thumbs up, thumbs down, whichever way you want to toss your hat into the ring. All right, we've had a few votes. We can go ahead and take a look. All right, so we have to compare all of our buckets. So at the 50 level, 55 to the right, everyone to the left is less than 50, so we're good. 55 has a leaf, so that's nothing to really look at there. 45 root, 25 to the left, 42 to the right. Oh, we have a problem. All right, this root is not happy with where its children are. All right, so this 42 node does not belong over here to the right of 45, right? 45 says all my children that are smaller should be to my left. All the children that are larger should be to the right. So let's take a look at this at another way. Right, so when we're building our binary search, we're building from the root going down. So when a new data point comes in, right, so if a data point X comes in and it compares, what range of values can X have such that we want to push that new data point to the left? Go ahead and type whatever you think it might be in the chat window. What's the range of values? Greater than 0, less than 100, negative 50. If X were negative 50, would it go to the left? Right, so I've got X less than 50. Anyone have a different range that we want to consider? All right, so right now we've got X less than 50 as the criteria for any new data point to go left starting at the root. All right, so that brings us down to the next data point. If we completely ignore 45 being in a tree already, so we'll just focus on this subtree with 45 as its root. What's the criteria for a data point to go to the right subtree of 45? All right, X greater than 45. Greater than 45. So we have now 2 conditions for, and let me get my eraser. 2 conditions for a value to make its way into this subtree. We have to be greater than 45 and we have to be less than 50. Right, so our immediate for any given node, our immediate parent and grandparent are going to form a boundary range for which new data can find its way into this tree. And I'm using whole numbers here, but we can assume floating point numbers. So 45 to 50 exclusive will be the range of possible values that belong in this subtree, and we can see 42 is falling outside of it. So this root of this 45 subtree is going to say I'm not in compliance with the rules of a binary search tree. And I'll grab a screenshot of that. Right, so if we were to look at any of the branches that we can grow, and let's get our shapes. And so there's several branches that we might be able to grow for our tree here. And only so much space. Be careful here. All right, not exactly clean left to right, left to right drawing here, but do. And let's see if we can make all this bigger. That looks a little better. All right. All right, so starting at the root, if we're greater than 50, we're going to come over here. For less than 55, we're going to come over here. All right, so we have our range of 50. And let's just do a text box underneath. All right, possible values that might end up in that subtree, 50 to 55. All the way over to the right, we would have values greater than 55. All right, dash, comma, whatever. 55 and infinity, which we'll just use as dots because I don't want to try to figure out where we might find infinity. So now what's our next range, right? We're all in the left side, so negative infinity. For left hand side, what's going to be our upper bound going to be? All right, over to 25. And for, let's call these boxes A, B, C, D, E, and F, so we can have context. What is our range for B?
25 and 50.
All right, 25, 50 is close, but we have a more immediate parent than 50.
55.
All right, so 45 would be our immediate parent. And over here, we're broken, so we're gonna have to, let's change this so that we're not broken. 48 would be a valid value. Let's see, is that one, I think. All right, so again, to get here, we have to be less than 50, so 50 would be a bound, but before we get there, we'd then now be less than 45 to get to 25. So our immediate two parents for this subtree will specify the range. So the same thing is going to apply for C, the immediate two parents. So we have 45 and 48. So 45 and 48 will be our range there. And 48 and 50 here. And immediate two parents does have an extra caveat of being a left and right parent. So our leftmost immediate parent and rightmost immediate parent. So let me give you an example of what I'm talking about. Okay, so let's add in a value here. If we're only dealing with whole numbers, we're pretty much constrained to 49. Let's just make it 49.5 so we can establish context of full number range. All right, and we want to establish the ranges that we might have. For the subtrees that we can grow here. Right, so then the next root that might form inside this triangle is going to be bound by its first parent, which is relatively to the right, and the next parent there, which is relative to the left, so 48 to 49.5. An exclusive range, so 48.1, 49 flat, 49.2, all those values would end up in the subtree. Right here, we can't bound the range as we did before because these two are binding the range of this subtree. So our first parent is to the left. Now that means we need to dig to our first parent that goes back to the right. So this binding range All right, so on the left-hand side, we have 49.5. That was the left parent, so it's going to find our left boundary, and then our right parent will be 50. All right, so I went up right branch, then I went up a left branch relative to the parent, and that's what we'll have to establish our boundaries for our data ranges. Right, so if I give you a tree and you're testing the values, do it two ways: just look at the root of the tree and then look at every data point in that tree and make sure it meets the criteria of less than that root for both sides. Or you can do it from a node basis, do it from the reverse and look at, so say I put a value in here that's 15. All right, so we look at a right parent and we look at a left parent and see, is that number bound by my ancestry? And if it's not, then we know that we're in the wrong place. This sort of makes sense. All right, so the values that would form these ranges would be values from our ancestors, because that was what drove us to being where we are. Right? Lesser values move left, greater values move right. And since that's the mechanism for which any value gets into the tree, the mechanism also drives the range of values that can be in any position in the tree, whether that position exists or is yet to grow. Duplicate values in a binary search tree. Generally, we don't allow duplicate values, as it will degrade the tree structure, causing us to have branches that can never grow. So let's do an example of that. Say we did want to have duplicate values because our data has duplicate values and we want to use a tree structure, a binary search tree. right? We'll have to decide where the duplicates are going to go. Do they go to the left? They go to the right? It's pretty arbitrary on what our decision is going to be, but let's say we decide to have things go to the left. And then we come along add another data point. Say we added 10. And now we want to add 15 again. So we decided that 15 being a duplicate, we compare. Well, duplicates go left, so it sees 15, duplicate go left, 10. 15 is greater than 10, so it'll go right. And here we have our tree. So let's look at our ranges. And see what we might have. Let's get rid of that. As valid values that we can grow. Same analysis that we were just doing. So for our first tree, A, or subtree A, what values can the subtree A have in it? It does get a little bit wrinkly here with that duplication, right? We know it's less than 15, still less than 15, less than 10, and then that's the leftmost subtree. So we have our range, less than 10. All right, so infinity and less than or including 10 since duplicates are going to our left. For B, all right, so let's go ahead and look at our right and left parents. So I have a right parent of 15. So that'll form the right side of our range. And we have 10. The left side of our range will be exclusive on 10 because if we get another 10, it wants to be in the A subtree. And we'll be inclusive on our 15 because we're having our duplicates go to the left. And then next up, we have the C subtree. So we have on our left, 15. All right, so we have left range 15, and then our right parent, also 15. And then duplicate 15s are already covered on the left-hand side, and since 15 is 15, we have the range of 15 to 15 exclusive on both ends, also known as a null set in our case here. All right, so we can try to squeeze 15 in here, but if we're just saying our duplicate values are going to the left as our resolution mechanism, then they're not going to fit. It would definitely be a little bit of a better resolution mechanism just to have all of our duplicate 15s over here, but that's just happenstance because this 15 might have been an 18, in which case our range would have been 15 to 18. So our problem still exists in the tree. We just have a high level of duplication here. And I can go ahead and copy and not have to change anything for D because it has the same circumstances. Left parent, right parent, both 15. The duplicate values were working their way left, right? 15 only lands here, right? Square bracket is the inclusive notation. Means we can go to and include 15, right? So we can go to and include 10 here. And then our last range, 15 exclusive, and then infinity. All right, a billion comes along, it fits in there. However large of a value that is that we can represent inside our node structure, that's as high as we can get to over here in that tree. So empty branch can never grow, an empty branch can never grow. So lots of empty branches. And empty branches will lead to poor performance. Right? You can always, if we do so on a binary tree structure or binary search tree structure, to be more precise and allow duplicate values, we can certainly accommodate it, right? It's programming. There isn't a real problem that you can't solve. It's just a matter of what needs to be done to solve it. What extra memory and processing power needs to be thrown at the problem to make it work. And sometimes some problems are so hard that it will take it an eon or two to actually solve the problem, but it will continually make progress on that problem. And here, right, so we could add an additional link, right? Star next or whatever we want to call it. That is just a chain of duplicates, right? A linked list. So we'd have little lines growing off to the side. So if I were to actually redraw it, right? So 15 came along. So this 15. Let's break my lines. All right, little list off to the side here for that other 15. Break some lines. This other 15, right? So just a single linked list. Going one way for all of our duplicates, and then 10 was our only other value. In the tree, so we can get rid of these other potential branches, and we now have a tree structure that doesn't grow quite so horribly. And we do the same thing over here. We got our 10 to 15 range as specified by the parents. Actually, attached, no, I didn't think so. All right, so there's always a solution. But we do need to adjust our node structure to account for this. All right, so if you look at our binary node structure, right, we have our data field, we have our left pointer, we have our right pointer, and then we have our next pointer or duplicate pointer, whatever we want to call it. Duplicates. All right, it's a variable name, somewhat arbitrary. So if an additional 10 comes along, 10 is less than 15, 10 is 10, added to our list of duplicates, and we're done. If it's not an existing value, we go left or right as needed. And we can solve for it. It just makes our node structure more complicated. And you know, when we do a search and we want to pull someone out or send someone back, right? Or do a traversal and we're processing the node. Okay, well, I guess we have to spit out all the 15s and whatever data is behind it. And again, when we're talking about, right, 15 is just an arbitrary value, and usually it's going to be some sort of key value. It might be a student ID, employee number, row in the store, whatever that data represents. Usually there's going to be more data that also exists behind it. It's not always the case. Sometimes you have like just a hash set that's just the values, right? You might have like social security numbers that you load in the system and you're just checking to see, is this number registered? Yes or no? Well, if it exists in the set, it's registered. If it doesn't exist in the set, not registered, sort of thing. And you don't actually have any secondary data points behind it. But usually there's going to be additional data points behind it. And this is just some key field. And typically key fields are unique. So most data structures are going to be building on top of that uniqueness, but not always the case. All right, so we're always building top down. Building top down, right from the root. And best case scenario, adding to a binary search tree, it's going to be big O log n. All right, average case, go n, and then worst case, big O of n, because we can have some really ugly binary trees. Let's create one or two. All right, so 15, if 38 comes along next, that goes to the right. And if we have 27, that goes off to the left. And 24 wants to join the party. That'll also go off to the left once I change the value to 24. And then 26 pops along. We started at 15, we went right, we went left, we went left. And then we went right. And then lastly, still have room to make this taller and use an integral number, 25. Right, 25. So if we want to test, 25's right parent is 26, left parent is 24, it's in range. 26, left parent 24, right parent 27, it's in range. 24, right parent is 27, left parent is 15, we're in range. 27 is 38, 15 in range, and 38 has 15. So everyone is quite happy with their relation, but this is a no better than a linked list. And linked lists, as you might remember, didn't have linear operational time. Complexity. So we need to get this tree a little bit more squat. Yeah, one example is good enough. There's lots of ways you can make an ugly binary search tree, but still binary search tree. If I want to find 24, I can find it. If I want to find 2, I can tell you it's not there. Right? It comes to the root. Go left, we hit the dead end, so it's not there, right? So searching the tree, we start at the root. Compare values. If left, if less, if the key is less than the root value, traverse left. If greater, traverse right. Otherwise, it's a match. Turn back node data. Stop. When we get a match, or find an empty subtree. Right. Much the same code as the insert, except this time we're looking for the data instead of trying to add the data. Now, deleting binary search tree. There's different ways of doing this, but what we're going to want to do is utilize a, well, let me go over the scenarios. 3 different scenarios. For the node that we want to remove from the tree. First scenario, the node is a leaf. Here we just delete the node, right? Correct parent pointer to null. The big O for searching is going to be linear. Thank you. big O, N. Because the standard binary search tree is not guaranteed to be balanced. But best case, big O 1 if it's the root, or big O log N for values at the lowest level. All right, this will be the root. All right, scenario 2. The node has a single child. Here we're going to go bridge across the node and delete the node. Third scenario, the node has 2 children. Here's where we have different ways of doing it, and what we're going to cover is the delete by copy. By copying. All right, so we'll get into that. So let's look at doing some deleting. With data, so make sure that's still a binary search tree as we're going along. And we'll just create a bunch of nodes here, and we'll just start blowing away leaves. 24 is in the root, 12 and 45 are its children. 45 has 31 and 61 as its children. All right, so we want to go ahead and delete 12. It's easily done. All right, 24. We'll need to have its left pointer cleaned up, but we can just go ahead and blow away the node and clean up the pointer to represent this as an empty subtree. Not a whole lot to do. We want to keep on deleting leaves. It's not a problem. I want to pop away 61. Same thing as before, which need to clean up the link that's pointing to it, so we don't have a dangling pointer, because dangling pointers can cause potential failure at runtime. We're only 1 leaf here to delete, so we can knock 31 off. And not much to do to the tree. All right, 1 leaf. Blow it away, and then the root, set the root equal null. Delete the node from the heap, and end of the story. All right, so there we have leaf deleting. Now we'll go ahead and delete nodes with a single child. All right. So we'll need a few more data points in here so we can actually have scenarios that meet the criteria. We'll add 5. That's less than 24, less than 12, so it goes off to the leftmost edge, and we can add 80. So we'll have another delete scenario. All right, so we're going to go ahead and mark say that we want to delete 12. We want 12 to leave the party, and whichever subtree, whichever side the subtree, the one subtree that 12 had is, it just gets promoted up the tree and becomes the replacement child. All right, so 24 had 12 as its child. 24 is now taking 5 as its child. And we're still in the binary search tree. So if we check, Right, nothing's changed over here in the 45 subtree, so we can ignore that. Look at 5, rightmost parent is 24, that's greater than 5, and there's no leftmost, so we're within range. If we want to delete 61, and this is just going to be a mirror scenario. '61 has one child. This child's on the right side instead of the left side. That's what we had before. 61 goes away, and we will relink 45. So instead of 45 referring to 61 as a child, now refers to 61's child. This time I was on the right side, so we're updating a right pointer. So we need code logic to know which pointer we're updating on the node who is having its subtree altered. Right, so before we altered the left pointer, 24, and this time we altered the right pointer of 45 to have it refer now to 80. And there's a special case if we're deleting the root, right? Because we need to move the root pointer, right? So if we say there was no 5 and we wanted to delete 24, okay, set 24 in a temporary pointer, pull it away, but there's no left or right pointer of a parent to update because we're deleting the root. So the root now becomes just 45. All right, deleting a node with 2 children. And as usual, get ahead of myself. And I want to add a few more data points in here. Let's add, what do we got there? 29 fits and 70 fits. So 45 marked for deletion. So we're not going to delete the node. What we want to do is copy in a value from one of the subtrees of the node we're deleting from, such that we can go ahead and simplify the actual node deletion part. So this node will stay around. And what we want to do is steal data from one of the subtrees here. Each subtree is going to have a single value that's going to work best for the copy. All right, so what is true of all the data points in the left subtree of our orange node here? What range of values could exist in this subtree? I remember 45 is what was there before. What range of values could be in our subtree here as circled? I put everybody to sleep already. No one knows our numbers anymore.
31.
Right? 31 and 29, those are values that are there already. And what's the full range of values, right? We can get 30, right? 30 is less than 45, 30 is greater than 24. Right? So on our number line, full range of values, 24 through 45. All those values could possibly be in this tree exclusive. Now, if I tried to copy 29 up here, would 31 be happy to have 29 as its parent? All right, not happy. All right, so we cannot copy 29 over there. It's not a good candidate value. So from the left subtree, there's going to be one candidate value that is going to work the best, and that's going to be the value that's closest to 45. The value that's closest to the 45 is going to be the rightmost node. Right, so the rightmost node in the left subtree is the best candidate from that subtree.
Wait, can you explain like why we can't use 29?
Because it's by a search tree and we can't have 31 in 29's left subtree.
Okay, thank you.
We're going to have a similar situation on the right-hand side. If I can draw. All right. The range of values here be greater than 45. 80 is not a good candidate for the same reason, because then we would have 70 to its right, and that's an improper relationship. So from the right-hand side, yeah, that's, there we go. Here, we'll just go ahead and change right and left. Right, so now we want the leftmost values. That makes 70 our best option from the right subtree. Okay, so we'll go ahead and we'll look at both scenarios. All right, so if we choose, we want to screen grab of this, or I don't think those scribbles are particularly useful in the long run. I'll just grab one just in case someone says yes later. All right. Okay, so we're going to go ahead and choose rightmost from the left, which is 31. All right, so we'll take 31 away. And now this is where we want to do our delete. All right, we delete the node as we did before, and that subtree gets elevated. Is it possible structure? Let me go back to our previous slide. All right, so right now, go back to our original tree. It is possible that there is a subtree. All right, that's here. All the values between 31 and 45 could exist here. The way that we find the rightmost value is we just go left one time, and then we just go ahead and traverse down the tree until we find the right pointer is null. And they happen to be on the very first node that we're looking at. So there is no right subtree. So when we're doing this delete operation, we're in one of two scenarios. We're either doing case 2, we're deleting a node that has a single child, which is what we have here, 29, or we're deleting a node that is a leaf. So we've simplified by copying, moving one value in the tree elsewhere, and choosing a different node to structurally remove from the tree. We've brought it down to our first two cases. One of the first two. So let's show the same thing, but instead, all right, so instead of choosing from the left, we'll take leftmost from the right. And that is 70. So we'll go ahead and copy. $70 out. And we'll identify this node to be deleted. And it's a leaf, so all we gotta do is delete it and fix our parents link to us. And we've successfully deleted 42 from the tree, and it's still a binary search tree, right? Because we chose one of the two values that is the best surrogate or best replacement for the value that we were replacing. Everyone sort of following along with the logic of how 31 and 70 were the best two values. Right? Those are the two values that are closest to the value that we're moving in the tree from that point downward.
But isn't 29 closer to that value than 70?
Yes, that's a good point. 29 is numerically closer than 70 is, but it's not. It's been excluded because 31 is closer. So it's the closest of the closest values that can be used. Yeah, so I definitely didn't state that very cleanly. All right, so 3 scenarios. It's a leaf. Leaf just gets chopped off. All right, it's when we got, for some reason, we want to make the tree shorter, but we want to keep all the stalks on top. We have to go in and try to cut the middle of the tree out, and that just becomes difficult. So it'll be easier to actually just cut the branches off and then splice it back down below. Let's see. All right, so we've got inserting, we've got doing our lookup, and we have deleting. The traversals are as we talked about before, it's pre-order, it's in order, or post-order. In order is the interesting traversal here because it does produce our sorted list. So if we go ahead and do an in order traversal, on our tree, you can see that. All right, so we will start at the root. First thing we do is go left, get to 5, output 5 because there's no left subtree. All right, bounces back. The right subtree bounces back, get back to 24. And 24's left subtree has been processed, so we'll spit it out. Traverse, get to 70. First thing we do is go left. 31, first thing we do is go left. No left for 29, so we can output it. No right for 29, output it. 31, 31's left subtree is now completed. 70's left subtree is now completed. Move along to 80. Knock it out. Work our way back up, and we're done. All right, so we have 5, 24, 29, 31, 70, and 80. As our in order traversal, which is ascending order. All right, we do pre-order and get 24, 5, 70, 31, 29, 80, but it looks more or less random. in that case, so it doesn't really much provide value for anything. But having a sorted list is useful, especially if we want to rebalance the tree, right? We should go ahead and generate a list. So we're list from the existing tree, and then we rebalance by pulling middle values, make 29 the root, 5 and 24 go to the left subtree, 31, 70, 80 go to the right subtree, 70 will be the root of that subtree, 31 and 80 on its left. So it's gonna be nice and balanced, and it's gonna be as balanced as we can get 6 data points to be.
I have a question.
Mm-hmm.
So we're saying that when we're deleting a node at that level there, it's either 31 or 70 can replace that area.
Yep.
But if we were to say on the test, you ask us to delete a node and which value we need to select, would that mean that there's two right answers, or we
Yes.
have to read the
So
context of the question
yeah, so I could
and
say
see which one?
if I would say, right, if I'm deleting 70 from this tree, what values could replace 70 from the tree? Then you would say 31 or 80.
Okay.
Right, so there'd be like 2 boxes to enter the values in, or it's just a multi-select answer box where I just list all the values that are in the tree and just check the 2 that apply.
Gotcha. Thank you.
Right, and the question can be asked in different ways. So if I'm deleting 31, which node has its state changed? Right, the answer there would be 70 because this pointer would change. And that's part of the state of node 70. Yeah, well, you could do a reverse sort just by doing a reverse traversal. We go right to left instead of left to right. But no, we were doing left to right, which is the conventional way of traversing a tree. Okay. Let's see. Let's take a look at our syllabus. Feels like we're almost in March or February. Right, work on the traversals. Okay. All right, let's go ahead and take a look at our binary search tree lab. Okay, so let's work on this lab, see what we can do in 10 minutes, and we'll take a 5-minute break. So we'll come back at 35 after. Here we're just doing binary search tree. All right, and node class, data, 2 pointers, and a tree class, 2 methods that we are required to have. Adds whatever data point, right? You can always have more methods if you need, but these are the ones that you need to have a minimum of. Add adds in sort of order, so if it's less, it goes left. If it's greater, it goes to right. And print, which is going to use in order traversal as its mechanism. Right, so the array-based lab we did a week or 2 ago, that one was pre-order. Now we're going to go ahead and toss in the in order. And there's not a whole lot of difference in the code. This one's, of course, link-based instead of array-based. But any questions on this one? Some of you, I see some of you already have it turned in, maybe more since I last created. All right, so we'll be back in 15. Go ahead and pause and mute.
I have a question.
Yep.
So we should do the deleting part in the binary search tree as well.
Nope. Well, you can if you want to, but it's not a requirement of the lab.
Thank you.
All right. Let's dig deeper into our binary heaps now. All right, again, we have min heaps and max heaps. We're the smallest at the top. Or a max heap. We have a max heap, the largest at the top. I have two properties or characteristics. Properties, characteristics, heuristics, if I can type, that defines a heap. We have a shape property, which means it's a binary tree where we build the tree from the top, level by level, from the left, which is sometimes known as a perfect tree. And we have the heap property. And this is defines the parent child data relation. Okay. Now, implementation wise, we will be using an array to store the tree. Reason why we're doing that is due to wanting to build the tree level by level without any spaces. This location in the tree is easily found by using the count, the current count. All right, so we're going to go ahead and be using arrays here. So we'll go ahead and have data be over 25, 30, 27, and then we'll go for 26, 14, 28, 40, and go for 12. And we'll say it's a min heap. We'll have 2, 4, 6, 8 data points. Just leave one extra. Data and index. Right, this should be state index. All right, so our first state after adding data, 25 is in the root. All right, so remember, root is at index 0 with array-based trees. Left child at 2 times index plus 1. Right child at 2 times index plus 2. All right, so our count after adding, which will also be our state number, is 1. So before we got here, our count was 0. We dropped 25 at index 0. There's nowhere else for it to go, so we're done. So right now our count is at 2. 25 already exists in the tree. So at our current count, we're going to want to go ahead and drop 30. 30 is going to then check its parent. Its parent's 25, which we can get to with an array-based tree. Link-based tree, we can't do it without adding back pointers. But we could do a link-based if we want to. If we want to add back pointers for children, so we add a parent pointer. The points are the way back up the tree. Certainly possible. It's not too big of a hassle to add that. But here we can do it mathematically. All right, we take our index, do a little subtraction, cutting things in half, integer maths, we throw away any remainders, and that gets us to where we want to be, right? So parent, let's see if I remember my math, equals index minus 1 divided by 2 equals parent index. All right, so if we're at index 1, parent index is at 0. If we're at index 2, parent index is 0, right? Because 2 minus 1 is 1, 1 divided by 2 is a half, and no room for the half, so that's 0, and so on. All right, so we look at our parent. Our parent is 25, and we're happy with that relation, so we're good to go. Our count goes up to 2. All right, so our count's presently at 2. So to get to state 3, we want to add our next data point, 27. See who our parent is. Parent's at index 0, parent's 25. So our relation's good. Nothing we need to do. Increase the count to 3, and we're done. To get to state 4, we'll go ahead and add the next data point at that count. 26, right? It's parent. We're at index 3. Parent index. All right, 3 minus 1 is 2. 2 divided by 2. 1 is 1. All right, so our parent is 30. 26 and 30 are not happy with that relation, so they're going to go ahead and swap. Then 26 looks at its parent and sees it's good, so we're done. Count goes to 4. Next up, we have 14. And copy paste, change that 3 to a 4. Right, 4 minus 1 is 3. 3 divided by 2 is 1.5. No room for that 0.5, so we're at index 1. So 14 sees 26 as its parent. It does not like that relationship. So we're going to go ahead and do a swap. 14 trades places 26 or moves its way up. 14 then looks at its parent, 25. Does not like the relations. We do a swap. And things that moved up the tree, right? And we'll just redo this as a linked base tree, which wouldn't be how we would represent heaps. After we're done, just get a sanity check. And 14 has now been added after moving its way up a couple of times. Count goes to 5. Next up, we have 28. Right, so we're up here at index 5. 5 minus 1, that's 4. 4 divided by 2 is 2. So 28's parent is 27. We like the relation. Count goes to 6. We're good to go. Next data point is 40. That's a funny looking 40. Let's try that again. Over here at index 6. 6 minus 1 is 5. 5 divided by 2 gives us, again, 2. Right? We'll see that parents, should we have 2 in a row, right? Because 2 nodes will have the same parent. At index 2, we have 27, so 40 adds without having to go anywhere. Last up, we'll have 12. Right, we've had 2 2s. Now we can move along to our 3. Parent, index 7. All right, so 7 says its parent is at index 3. 12 doesn't like 38 being its parent, so they'll go ahead and get ahead of myself. They're going to go ahead and swap. 12 and 30. 30 bubbles down. Another way to look at it. 12, which is at index 3. Index 3's parent is 1. See 25. Problem again. So 12 and 25 will be in new position. And one more time, because 12 does not like 14 as its parent. So we'll go ahead and have a state change there, and now we're done. So let's go ahead and redraw this tree as it just from the final state. And then we will go ahead and try screen grab of that first. All right. So our first node is our root. Next two data points would be the next level. 14, 27. The next two data points would be the first two children of 14. So we have 15 and 26, excuse me, 25 and 26. Next two data points, 28 and 40, the 27's children. So we'll drop those in, 28 and 40. Two most exciting numbers in the tree, because it's got to be somebody. And then 25 has 30. Right, just keep building level by level. Just read down 12, 14, 27. Keep on reading down, and that's going to be the data in our tree. All right, so it's easier to see here if we go ahead and trace through. Trace through, right? 12, 14, 25, 30. Nice ascending order. 12, 14, 26, 12, 27, 28, 12, 27, 40. Right, all of our paths from root to leaf are ordered as should be expected for a heap. Of course, we don't have any left-right relationship, right? This would not be a binary search tree that we have here. Right, 26 over here is happy with most of these values, except is not happy with its parent. Right, 25 being over here, not happy with both of its parents. Right, it's not a left-right relationship, so just make sure you keep your structures separated. Binary search tree likes its left to right, and the heap likes its up and down. And so if we were to build the tree from a not linked or not array perspective, so build the same tree again. Start over. First data point is the root. 30 comes along to the left. It is happy with parent relations. We can go ahead and leave what is. 27, as we had before, I should update the data point. Makes for more accurate representation. So we're 27. 27 is good with 25 being its parent. All right, and we get 26 trying to attach itself. And here we have our problem. We're not maintaining heap order as we should be. So we'll have to do some moving around with our data points. to get us into proper heap shape. 26 compares to 25 and doesn't need to do anything. So we can go and stop there. Yeah, right, 14. 14 wants to attach itself, but that's not going to work. So 14 moves up. 26 moved down. And then 14 tries to squeeze in, but it's not going to land there. And it works its way to the top because it is the smallest value, right? Smallest value should be at the top of the tree. 28, 40, and 12 are next. '28 and 40 were the easy additions because they didn't have anywhere to go other than where we first want to drop them. All right, so 28 adds in without any hustle or bustle. 40 comes along, same thing. Right, so if we're trying to, if this actually was link-based and we're trying to find the right place, it's a bit of a digging around. So see the root exists, so that's not the lowest level, so we'll go ahead and try right. So there is a right edge. So we can go ahead and see 27. Okay, go try right. We can't go right. All right, so that maybe that's the right spot. 27, go left. All right. We went ahead and found where we need to go. We want to add 40 over here. Not too big of a deal. But next up was 12. So we'll do the same logic as we just did. I'm going to add 12. So, okay, let's find the rightmost position in the lowest level. 40. Okay, 40 doesn't have right. Does 40 have left? No, it doesn't left. Okay, so this is not where we're adding it. Go back up to 27, come down. Does it have right? Nope. Does it have a left? Nope. All right, well, that's not it. All right, I'll come back up. 25, does it have right? Oh, it does. Okay, nope, nope. Can't head there because there's no left. Or potentially not adding there. We might actually be adding there if 30 has two children. Or 30, no right, no left. It's just, if there's a good algorithm with this basic structure, I don't know what it is. Usually the solution is going to be, well, we can add sibling or level pointers where we have pointers that point along here. So there's pointers that point along there. So we can basically keep a pointer here and have back pointers so we can get up to the next level so we can change its pointer. It just becomes a significant mess. Right? All problems have a solution, of course, but some solutions are not quite as ideal as other solutions. So the ideal solution here is to have this be array-based because this being an index in the array is something we can get to immediately, right? That's one of the key advantages of arrays that we talked about in the past. We have random access. I can get to the root, or I can get to anywhere in the data section of the tree, or just beyond the data section of the tree in constant time, right? I can get to my parent just by doing a calculation. Where's my parent? What's the value there? Okay, don't like that being there. So we'll see. Will 12 fit in this hole? Nope, parent says 25. Will 12 fit in this hole? Nope, parent says 14. And will 12 fit in this hole? Yes, because it's got no further it can go up the tree. All right, so it is one of the rare cases that you'll find array-based tree being the more probable tree, but it is the way to go. Max heap's same thing, except largest is going to be at the top. So building a max heap is the same idea, except the largest will be at the top of the tree. Now, here's the part where people like to fall off course. And so before we get to the deleting, why are we talking about heaps? All right, and prioritization is one of the primary uses. Keeping a heap structure. All right, so we talked about priority queue briefly when we're talking about queues. Priority queue is an abstract data type, which means you can implement it in whichever way you want to implement it. It's just simply going to define the operations and expectations of the time complexities for those operations. And those expectations are based off of known implementations effectively. Right, so if we have a priority line, so these are people and their priority numbers. 12 has the lowest number, so they have the highest priority. They're the data point we're going to process next. 12 leaves the tree. And then the next number that's smallest in the remaining values will take over. So that's going to be 14. Right, so that deleting is where we're going. It's going to manage how doing that. So the reason we built the tree is so that we can very quickly get the next data point. In fact, we can immediately give it back and have a background thread come back in here and restructure if it takes longer to process the data than it does to restructure the tree. So it's depending on where bottlenecks are, implementation details can vary. And then 14 will be immediately available, or worst case scenario, logarithmic time. In fact, let's talk about that. A heap is a balanced tree structure. If we are balanced, then a single data point operation, such as adding a value to the tree, will be big O log n. Right, and I didn't qualify it, so that means worst case scenario. It's going to take log time. And the worst case scenario when we're building the heap is a value that ends up in the root. Right, in the best case scenario, we see the value, we see the parent, we do one test, and we're done. Right, so if I add anything, if my next data point here is greater than 25, it drops in here and it's happy. Next data point is greater than 26, drops in, done. Same story again, done. Greater than 28, 2 times, done. Greater than 40, 2 times, done. This entire next level of the tree could be built constant time per each addition if larger data points keep coming along, right? So if we build the heap with an already existing ordered data set, building that particular heap would happen in linear time. Right? In general, building a heap is going to be n log n because a single addition in the worst case is logarithmic time. Building an entire tree of n nodes is a multiplication factor. So you would have n log n. Because at most, we have to go the height of the tree, and the number of nodes is exponentially proportional to the height. All right, so I will swing back to that again as a separate subject about balance on the tree and how big the trees are getting. For now, it's log time when we're balanced. Right? And being balanced is one of the key characteristics that we want to see a tree having. Okay, so deleting. Deleting is done by removing the value from the root. From the root. Arbitrarily deleting value from anywhere other than the root is not a well-defined or well-supported operation. In a heap, heap is not a search structure. I want to find 30. I need to dig around a lot, especially since we can have duplicate values. Duplicate values in the tree. All right, so if I wanted to, I could add 4 30s. Let's see, 1, 3, 5, 7. I can add 4 30s to this tree right now, and they would all end up right all on that level, right? I want to add 30, happy. 30, happy, 30, lots of happy, right? Several more times more. And if I want to say delete 30, well, I'm going to have to look at every node in the tree. And then there's going to be a lot of work to be done here. A lot of work. It's not a well-defined operation, so we'll generally consider it to be a not supported operation to arbitrarily delete a value in the tree, or at least it's not a primary operation. Right, so the primary operations for the heap is going to be add, adding the value based off heap order and the shape property, making it as a perfect balanced tree, and delete, where that delete is predefined as deleting from the root. Trying to delete anywhere else could be a supported operation, but it's not. It's like peek for a stack. Yeah, you can look at the top of the stack. Or if a stack you want to delete some middle value, yeah, you could delete some middle value, right? We can code it to do it that way. That's just simply not an intrinsic operation to that data structure. So for deleting, we're always deleting from the root. All right, so if I come along on a test and I say, perform a delete operation, common question is, which one do you want me to delete? And then the answer is, I can't answer that for you because you're already supposed to know who to delete, and that's the root. All right. So we'll go ahead and create a vacancy at the root. Value there will be sent back to the caller. Since the size, the tree is shrinking by 1, in order to observe, if I can type and or spell, both of which are challenging, the shape property of the tree, the rightmost value on the lowest level will be outside of the data range. And so right now for the tree that we have at the moment, 30 is the rightmost node of our lowest level. So that is the one who's finding himself displaced. So let's set that there. Okay, so that value is going to try to fill the vacancy. Vacancy at the root in competition with the children of the root. For the min heap, smallest of the 3 will be promoted to that root. That promotion in turn will possibly make a vacancy, and we'll repeat until there are no gaps. Everyone still hear me? I see one of my applications complain about losing connection. Sound check. Just snore if you can hear me.
Yeah, we can hear you.
Okay. So let's do some deleting. Twelve's going away. So first step, Set 12 aside somewhere so we can send it back. So we create a hole. Next step, at the count. All right, so our count's 1, 2, 3, 4, 5, 6, 7, 8. All right, so we got index 0, 1, 2, 3, 4, 5, 6, 7, 8. So 8 is where the next data point would be. So just below that, so one less than the count. So we can shrink the count right away. 30 is falling out of the tree. So I'll give that another color. And now we have a fight for the next lowest value. So between 14, 27, and 30, the smallest of these values are going to be promoted up. "14 is the winner of that competition. So we'll go ahead and shift where our vacancy is. Vacancy is now over here. Make that the position for consideration, and these are now who's in contention. We're filling the new hole that is bubbling its way down. All right, and 25 wins. Between those data points. And we have a hole here, which has only one candidate. So 30 will go ahead and fill. And we've done one delete. 14 is now in the root. So let's keep on deleting. Delete again. Where are we? Okay. Just checking the clock. So as before, we will always and only be deleting from the root. "14 gets tossed into some temporary variable so we can return it, or we return it at the same time we spin up another thread, but whatever. 40 is finding it no longer fits where it was in the tree. And it is now in competition 25 and 27 to take over as the smallest. All right, so 25 wins, 25 moves up. And the competition shifts focus a little bit. Created our new hole, and we have the data points. So if this value were, say it was 29, no, 25. It could have been that. 20, it doesn't matter. We'll come to that scenario later. All right, so 26, 30, and 40. 26 wins that competition. And we will continue. And 26 got pulled up. Vacancy moved along. One player left in the game. And we finished getting rid of, leave that orange. Finished getting rid of, was that 14 that we deleted? Delete, delete, delete. All right, our third delete operation now. Misclick, misfire, hit the wrong keys. So many ways to go wrong, so few ways to go right. Okay. And 25. Getting ready to go. Go ahead and join a couple of steps this time around. 3 candidates to take over. And we're going to get this time what I was trying to show last time. So get good data set. All right, we have the void. Filling the void will be 26. That allows our void to move. These nodes no longer care what's going on. And this time 28 is going to jump in. And we didn't have to go all the way to the bottom of the tree, which going down a fair distance in the tree is likely because the values down going to be the greater in general than the values going up because of the ordering mechanism. So the value that we're displacing at the end of the tree or at the end of the data part of the tree tends to be on the larger side. So we'll tend to find that it sinks quite far, but not necessarily always going to sink to the bottom. Let's continue with the destruction. Yeah, we still have tree to delete. And what we're doing here is working our way towards a heap sort. So I'm going to skip a little bit more. And let's get the colors right. And all right. So 26 went away, 40 is falling off, 27 finds that it is going to win, and 40 is going to find nowhere else to go than there. So 26 left, 27 is leaving now. 30 finds itself displaced. 28 wins the competition, 30 finds its way moving up. "28 jumps ship, 40 falls off, 30 wins the competition, 40 moves on over to where 30 was." Wow, let's just make the same mistake more than once. Almost completely obliterated, 30 goes away. All we have left is 40. Take over, and then 40 gets deleted and the tree is empty. All right. And after the destruction is completed, we end up the heap sort, which is big O n log n. Not that. Let's put it like there. N log n. All right, so if we look at the data points we deleted, right? Going back to the beginning, 12 left. Then 14 left. Then 25. Right, so we had 12. 14, 25 left the party. All right, then 26 jumped, all by 27, 28, 30, 36, 37, 28, 30, and 40. All right, we deleted 8 data points, 8 data points. Deleted 12, then 14, then 25, and we have a heap sort. Right, the functional cost is 2n log n, so it's typically not actually used as a sorting algorithm, but it's one of the many, as we've seen in prior weeks and on YouTube and various things out there. There's a lot of ways to sort data. Quick sort is the common library implementation as far as I know. Not that I know all that many libraries. I just know C uses it, and I do believe other languages use it as well. It's whatever the library chose to implement, because some libraries might be specialized at different data scenarios than a general purpose library, so they might offer a different standard sort, and they might offer more than one sort, because not all sorts are created equal, and not all sorts handle various data scenarios equally well. Right, so deleting is big O log n, which is how we got to our heap sort being n log n, because we need to delete n times, and each delete is a log n operation. And it is this way because the heap is balanced. Okay, let's see. Back to 35, right? Okay, so any questions about the heap for a moment? Okay, let's talk about tree balance and size. Right, if we have an unbalanced tree, in the worst case, the height of the tree is proportional to the number of data points in the tree, looking much like a linked list. That gives us our big O(n) operations. If we have a balanced tree, such as we do with a heap, then the growth rate, the height versus the growth rate of the number of data points is going to be on a log scale. All right, so we go and build a table. Got heap height. And then we have the min, number of data points, max, number of data, and what the delta was from one level to the other. So height 0, right? So 0 height tree, right, means we have one node, the root, length of the longest path from the root to the lowest leaf, which is the same node. There's 0 hops. And no delta at this point. Heap height of 1. This level will require at least 2 data points, where we have a root and we have one value to its left and a max of 3. All right, so our delta is going to be 1 on the low side and 2 on the high side. Going up another level. To get the tree to a 3rd level, we need to complete the 2nd level. All right, so we had a 1-level tree here. We had a 2-level tree here. So in order for us to get to a 3-level tree, we need to exceed the max, because we're building level by level. So we cannot get a tree to be this tall until we have a perfect triangle above us. And then we've grown, and we can have as many as 4 data points here. All right, so we grew by 2 on the front and we grew by 4 on the back end for our min and max range, and that pattern will continue. We're going to be 1 greater than the max of the previous level, and then a base 2 growth factor here, which gives us a base 2 growth factor on both sides. All right, so there's 2 ways you can look at it. All right, 1 greater here, or in terms of the 2 to the H type thing and to the H type thing going on there as well. Right, so we can generalize this to, and we'll just, I can do it. I can do superscript, here. And this one, to H plus 1, all that minus 1. And some more superscript. And the delta here, oh, it's going to be this 2 to the H minus 1, whatever. Don't care. This, we're using this delta to drive at how we were growing. All right, so 2H plus 1 is basically saying go down to the next row and then subtract 1, and that gives us where we were here. Right, so 2 to the H, 2 to the 0 is 1, plus 1 is 2, minus 1 back and forth. We're just reversing it. Like before, we're adding 1 to get to the here, and the reverse is subtracting 1 from below to get to the one above for the max. And that's how quickly things grow. So we're doubling, pretty much doubling the size of the tree, but the height growing by a fixed amount. That's logarithmic growth. Everybody kind of with me there? Of course, it doesn't matter if it's a min heap or a max heap. Shape property is identical for both min heaps and max heaps. Thumbs ups are good. That's what's going to give us our log time. Balance is the key, and we're going to look at other balanced tree structures here as well. But before we do that, let's go ahead and take a 5-minute break. And we can take a look at the next thing, because there's always so much to talk about. So lots to talk about, lots of trees, lots of trees. Take 5. All right. AVL trees. I'm totally have to cheat. It's Allison, Valsky, Lewis, whatever their names are, but AVL trees, it's naming for Allison Landis. Yeah, I always say Lewis. Always so close and always so far. This is a self-balancing binary search tree. All right, so as we've been doing, we're building off same structures and adding to them additional rules for those structures. The addition here on top of it being binary search tree is that it is height balanced. All right, so being height balanced means the difference in the heights of the two subtrees of every node in the tree is no more than 1. All right, so don't care about the data at this point. We're just going to go ahead and look at balance. So looking at our first tree A, it's a single node tree. There's no other possible way for that tree to exist, so it's height balanced. The height of the left subtree and the height versus the height of the right subtree is 0. There's no difference in their heights. Our B tree, difference in the heights of our tree is going to be 1. And if we go ahead and add our D tree here, just going to be a mirror. For the most part, same thing. The difference in the heights are 1. It's good to go. And if we keep growing in a nice triangular fashion, we'll maintain our height balance. So let's fall out of balance. Only his roots will be X, Y. If I go ahead and add Z here to this tree, we're going to be unbalanced. All right, so there's 2 ways you can look at heights, right? This tree, right subtree of X has 2 levels. Left subtree of X has 0 levels. So the difference between 0 and 2 levels is 2. So you can also look at this in terms of the heights. All right, height of the left subtree, -1, and this being one of the reasons why some systems don't like the definition of height that we're going with. They want to go ahead and add 1 so that we have zeros instead of negative ones. All right, it doesn't matter. The relativity between the sides is the same. All right, so the height of the Z subtree is going to be 0. All right, so if I can get in there and type, Z subtree is 0. Height of Y's left subtree is -1. The difference on the number line between these 2 numbers is 1. So Y is happy with the state of its tree. Going back up, the height of Y is 1. So we come up here and X looks at the heights of its 2 subtrees. Sees the difference between these 2 numbers to be 2. And it is going to be complaining about being imbalanced. All right, there's several ways we can add data to cause it to become imbalanced, but does that make sense? How this is out of balance? So you want to count levels, you want to look at heights. Same measurement system for the most part, other than the actual numbers you're using. And that causes us to move away from, there we go. Being imbalanced moves us away from big O log n. So after adding a data point, as per usual, BST add mechanisms, per the usual mechanism, we'll trace our way back up the tree and check leg lengths for not being height balanced. There are 4 scenarios, 2 in their mirrors, that the trace may take going back to the node that reports the leg are too uneven, which we'll call the alpha node. We might be inserting into the right subtree of the right child of alpha, or the mirror, the left subtree of the left child of alpha, in which case we'll do a single rotation. We'll identify the child of alpha on the insert path as the beta node, and we'll rotate beta towards alpha. All right, so let's visualize that. We already have one of those scenarios. Grab it. All right, get rid of extra data for a moment. All right, so orange will go ahead and be alpha. And we'll do green for beta. So these are our 2 nodes. All right, so Z is our new data point. We added Z, which we can easily tell from here because building minus is top down. The newest data point will always be a leaf. If there's more than one leaf, you can't determine who is the newest of them, but the newest data point in a binary search tree is going to be a leaf. So we took a path from Z to Y. At that point in the tree, the Y subtree was happy. Then we went back up to X, and then X subtree was unhappy. So we want to go ahead and rotate Y pulls up the tree. X slides down the tree. And then we have nice balanced state. If we look at the values, we can see they're still following binary search tree, right? X is before Y, and Z is after Y, so we're in a good state here. All right, if we built the tree in a different order, we built Z, then Y came along, and then X came along, we would find ourselves that Z is not happy. This is just the mirror case. Mark that as alpha. Mark Y as beta, and it's the same thing. Beta rotates towards alpha. So Y and its subtrees move along. This is a simple case. I don't have subtrees, other subtrees to worry about. We move along and we get back to nice triangular formation. X to the left, Z to the right. It's the exact same tree as we have above here. It's nice and balanced. Triangular, like we want it to be. All right, the second scenario set is when we have a left, right, or a right, left insert path from the newly added node to the alpha node. All right, so on that path, alpha and beta are the same, and we'll add gamma, which is the child of beta on the insert path. So I'll add a little bit more color. Let's see, good color. That seems to be legible. All right, so we've got gamma joining the party. So instead of Z being our newest data point, we'll have X, Z already, and Y is going to join. So now we have a gamma party. Right, trying to do a single rotation here doesn't work. So let's go prove that out. If I try to do a single rotation where I move beta towards alpha, X is going to end up way down here because it's a binary search tree. Right, that just does not work. That's still imbalanced. And there's a bit of a not quite actually managing things properly to get X where it needs to be, but this is where X has to be because it's a binary search tree. It has to be to the left of Z, has to be to the left of Y. It's the only place that X can be with Z and Y as the root and Y as its child. So we did not solve our balance. This does not work. Let's see. There, just put it big there. Send that to the back. Let's try that again. Send to the back, and then we'll just color the box red. All right, that does not work. So we're gonna have to do 2 rotations. Y rotates towards Z. Right, gamma rotates towards beta. Z is going to have to move down for that to work. And Y is going to take its place. All right. All right, so even in this intermediate state, it's still a binary search tree of X, Y, Z, which is not balanced yet. And gamma will rotate for a second time. Y moves up, bringing its subtrees along with. And now we're balanced. And then we'll have the mirror scenario. Okay, let's get a more complex scenario. Complex single rotation example. Okay. And let's get there and build out a bit of a tree. M is nice in the middle of the alphabet, so we'll make that for a good root. And we'll start building up a little bit here. And change the data as is needed. All right, D, B, F, that one T, and M. No, leave this as an empty bubble for the moment. That's going to be our new data point. Adding to the right subtree of B, which I guess just leaves us C. All right, so C it is. So before we get here, let's make sure we have a binary search tree, as we should, because it's not a binary search tree. We're at a foundational issue that needs to be rectified, and it needs to already be balanced before we start adding more data. All right, so leaf, we're happy. D subtree, one level, it's happy. M subtree, 2 levels, 1 level, M subtree is happy, so we are balanced. The data is good. Everything less than M to the left, everything greater than M to the right. Same thing for D, less than D, greater than D. It's an AVL tree. All right, C is coming along. We want to add C. Let's put a dotted line. So we see that's our newest member. Work our way up. B subtree is happy. We have 0 and 1. D subtree is happy. We have 2 and 1. M subtree not so happy. We have 3 levels and 1 level. So M is going to go out of balance. D will be our beta node. All right, so it's the same as we did before, but we have more subtrees to worry about. All right, so as we do this, right, the D subtree is working its way up. The M subtree is working its way down. Right, so D wants M to become its new right subchild, but we already have a right subchild there. So F is going to have to fall off temporarily. So it's in a little bit of a limbo when we take over our former parent as now our child. All right, so now the question is, where does F go? So let's look back. Where was F? F was in between D and M. It had D and M as its parent and grandparent. That's going to be mostly the same. A little bit of role reversal. Its ancestors will still be D and M, except M will now be parent and D will now be grandparent instead of the reverse. So F wants to go ahead and move over here to M. So let's talk about that a little more, think about it. Well, we happen to have in my slightly more complex scenario, no left child for M to do that attachment. So let's take a look at this. Before we made the change, D was M's left child. that relationship is being discarded. D is becoming the parent. So we're guaranteeing that M has an empty left child because we've already taken that left child away, right? We came along there and deleted this relation. So we know there's going to be a vacancy here that will handle the F subtree, however big it might be. There could be 100 nodes in this subtree. After we did the insert, we found this is where alpha was. We do the rotation and we're good to go. Single rotation. Go ahead and mark this line as solid. Every level is pretty much as full as we might expect it to be, right? For a 6 node tree. Having 2 full levels and the balance on the remaining level is good to go. Right, and then of course you would have the mirror case. So I'm not going to bother doing that. But now let's get to a more complex double rotation. Reset our colors. All right. We'll add a few data points into our tree here. Let's add E. E goes there. Let's add H. H goes there. We'll attach our lines. Before we go carried away, just make sure we have a binary search tree still. All right. F's good. M's good. D, we have 2, we have 3, we're still good. So at this point, if D's right leg grows 1 taller, it will become unhappy with the lengths of the legs. So we can go ahead and insert anywhere in the F subtree. If we had room, we could insert here. Right? Using letters kind of paints us in a little bit of color, but if we go ahead and add G or we add I, J, K, L into our tree, it's going to work our way up such that we go from F to M to D, and that's going to be our right, left pattern and force us to double rotation. So whatever we'll add K doesn't much matter. We're a little bit far removed. K is being added. All right, and actually let me add one more data point because no, that's fine. No, yeah, that's good. M will be the alpha. It's actually good. Covers the second point to call out as well. Okay, H subtree is good. 2 node tree is as good as it's going to get. F subtree, 1 and 2 levels. That's good. M subtree, 3 and 1 levels. It's not good. All right, so here's one of the mistakes people sometimes make. They'll go all the way to D. Right, so D is also not good as I was building up towards. But before we even got to D, we found a lower node that's not good. So trying to fix things at the D level is not going to help this subtree. So we need to fix this subtree, and by fixing this subtree, by making this entire subtree shorter, shorter, that's going to make D happier about how long the leg is on the right-hand side. So M is our alpha node. F is our beta node, and H is our gamma node. So we're going to have to do a double rotation. In the double rotation, gamma is going to move, and it's going to move twice. So our first movement, bring H up. Bringing H up is going to bring F down. And if F would take its children with it, that would be nice. All right, so as we had before, doing our rotations in this interim step. We want to make sure that we still have a binary search tree, because if we don't have a binary search tree, we did not rotate properly. So EF's good, HFE, HK is good, M. Right, this is all we know it works. So we're still in a good state. So we can carry forward. And gamma will rotate again. M subtree will move down. H subtree will move up. And like before, things will fall off. All right, so K falls off as we're doing this. Oh, yeah. All right, like before, the ancestry is going to remain the same. K has only one place that it can go. Its parents, being H and M, are still going to be parents and grandparents. H and M, because K exists between H and M in the alphabet. All right, so let me go ahead and line things back up here with our other cousins. And let's recheck, make sure things are properly balanced. All right, EKT leaves, goes, MKT balanced, and data's good. EF is good. Now H, we have 2 and 2, so that's good. Less than H, greater than H. And then working our way back up to the root. We don't really need to, but just to check. 2 levels, 3 levels, we're in range. Right, the tree is definitely not as balanced as, say, a binary heap would be, right? Binary heap is like, oh, you got a little bit of a space over here, but it can only go so far before some sparseness on one side is going to cause us to rebalance with a rotation. And then that's going to push the sparseness down the tree. So we're going to be log time for our rate of growth. Getting close to the pure log is a little bit further off here with an AVL tree, but it's going to stick close to things. And since the insert's on a balanced tree, the insert's going to be logarithmic time, which means searching is going to be logarithmic time since the tree is balanced. Inserting is big O again, and searching is big O again. And we're not going to bother getting into deleting, but should still be on the same scale. Similar logic as we would have deleting from the binary search tree is just we have the extra check of, well, I deleted somebody. Did somebody get shorter, and then that shortness cause imbalance to occur? Because if that imbalance occurs, we'll have to do rotation. Let's see. 20. Okay. Let's see. As mentioned last time, since we had a holiday last week, we had soft dates for these items. So you still have until tomorrow night, if you still haven't done these, to get these in for full credit. And then the items we have the min heap. Right, it's an exercise. It's what we talked about, dealing with arrays, calculating parents and children. Those are definitely good places to add little helper functions for to get those indexes. But when you're dealing with an array, the boundary checking tends to be a little bit annoying dealing with arrays, but it's a heap, so heaps are array based. Period. End of story. There's soft due date for that kind of app? Nope. Everything else is good to go. Right, binary search tree. quarter of you have already done that one.
I have a question.
Okay. One
Isn't
second.
the test to practice is published there?
Yes, that's published as well. I pushed it earlier this evening. So this is available for you to check out. We'll take a look at that really quickly here in a minute. All right, in program 2, hopefully people have been taking a look at it. This one is potentially easier than program 1. The trick here is getting around or disassociating this with a doubly linked list. This program 2 is not a doubly linked list. It's a doubly ordered list. So the node structure looks like a doubly linked list node, just like it looks like a binary tree node, in that there are 2 pointers. Right? So we have a data field and we have 2 pointers. It's very much like a singly linked list because one pointer tracks the next person by their name, and the other pointer tracks the next person by their weight. Right? So, and the other thing that people like to fall down on this one is try to make it 2 lists. It's 1 list. So if we have 3 people, there are 3 nodes. So when you build the list, when you add a node to the list, you're adding 1 node to the list. We should see 1 new keyword. And then you go through and maintain 1 set of pointers for the next name pointers. And then you go through and maintain the next weight pointers. So at any point in time after adding a person, after that function is completed, we can call print, printing by names, Abe, Michael, Tom, or printing by weights, 150, 200, 275. All right, so what you want to do is you want to go to your singly linked list lab code and use that as a starting point. I recommend using weights first because it's numeric and it's easier to work with numbers than it is to work with strings. And make it a sorted linked list. I think that the lab for the sorted linked list was an exercise or was turned in. Whatever it is, that's a good starting point for program 2. After you know that's working, go in and add the name to your node type. And then add logic to your add method to maintain the other pointer. All right, so you'll add the name, add the second pointer, and then add logic to add and add another print method. All right. Just go ahead and print the list each time someone's added, so it's easy to see that things are growing correctly. And that's what there is with program 2. Questions on program 2? And one person's done. Hopefully more of you have started on it after I announced it last week, but you know, when we don't get in class, things tend to get pushed off. Anyways, moving back, practice test. As usual, it's going to, some of it's just description and the answers are, hopefully this still works. I always have to create the answers again. It's always fun when links break. And it's right. Answer to those parts are there. And of course, auto-graded. Whatever the numbers are, just type your numbers in. Whatever your numbers are. Numbers. That's right. Or yeah, just saying, read the code, which sort is it? I'm just arbitrarily selecting things, typing numbers, selecting things, whatever. Right. This one is insertion sort. So you just identify where the algorithm went wrong. So which of these rows did it go wrong? And it's based on the state changes based on the previous line. So if it made a corruption on line 3 based off where things were from that corruption, did it keep going correctly from that point, or did it fall down? All right, so if it's squares, multiple answers could be the case there. Right code. Who swapped sort of thing. Insertion, right? Who swapped? Whatever. Whoever swapped. Merge sort. Right. For this one, just basically do the merge sort on paper and look and see what doesn't line up. Right. So do the first state change. Right. Split in half. Do the swapping and just look at what doesn't match up with your state changes. Right. Quick sort. Right. There's 3 ways to get the pivot. One's just use the first one. One's use the one in the middle. Whichever is middle. Yep, that's the middle. And then the other one's the median of 3. Just doing a little bit of math. And just select whoever it is, and it will auto grade all the good stuff. So you see the answers in case you're wrong. If you don't understand why you're wrong, just go ahead and post a screenshot of the question. Hey, I guessed right on one of them. Of course, here I got no points because I had more wrong than I had right. Et cetera, et cetera, et cetera. All right, and your math, of course, is always fun. Any questions about anything?
So I have a question.
Mm-hmm.
So we are not gonna do an exam about like big O notation and function notation for this test.
Well, big O notation is always present. Well, it's not always present, pretty much ever present throughout the whole semester, but no, we wouldn't be doing functional notation. Right, our subject areas, right, this is our reverse push, all of the sorts that we talked about before tonight, recursion, multi-dimensional arrays, double linked lists. Right, so you need to know bubble sorts, big O and squared in the worst case. Remember, again, as always, big O is worst case unless otherwise qualified. So if I ask what's the big O for bubble sort in the best case, right now it becomes big O n. Right, so our O notations for our algorithms where we discussed what the O notation is always something that I could ask about. Right. When we do the row major ordering, we didn't get into the O notation there. It's pretty much, it's constant time. It's just a mathematical equation. It doesn't matter how big the matrix is. The number of dimensions causes there to be more math, but the size of the dimensions, which is going to be the primary driver of how big they are. And then just, right, we had a brief part on double linked list for test 1. Test 2 is a little bit more, we more likely see code and stuff like that here. And recursion, which we're going to keep playing more and more with in trees and other scenarios. Any other questions? All right, so more trees to talk about next time. So next time we'll take the test, keep talking about more trees. And
So it's gonna be until the chapter 3.
oh, the chapters. Let's see. Chapter 3 is just container classes. So chapter 4 didn't know. We already did that. Right, chapter 5 linked list for as and it counts for double linked lists. Okay, stacks keys we already did. All right, chapter 9.1 specifically is recursion. 9.2 is the case studies. It's always good to read the additional parts, but I'm not going to ask about the specific case studies. And then where's all our sorts? Searching we did already. There's our sorting, chapter 13. All right, selection sort. Merge sort, quick sort. Sure, bubble sort's in here somewhere, but I don't actually have the book handy. Heap sort is not on this test. That's a tree sort, so we say that for the trees test. All right, so we'll roll on to our break in lab time to wrap things up. Next, we still have like 25 minutes of break. So I think brings us down about 9:25. So we'll use the balance time for lab. So I'll keep floating around in case you have questions in our lab, but I'll be going on mute and I will stop the share. That's all the lecture for this evening. Have a good night. Don't forget to study, get your coding done. See you on Monday.
Thank you, Professor.
Thank you. Bye.
And no trees for test 2.